Here's the theory part of our separating acids and neutral compounds by solvent extraction lab. So effectively, hopefully by now you know what we're doing, but we are doing the macro scale separations, which separates a mixture of compounds by washing and extraction. We'll talk about what that is later in our discussion. This takes advantage of different solids solubilities, as well as different liquids densities. We use this technique to isolate solids completely, and then we will collect masses and assess purity by melting point when it's compared to literature values. The assessing purity part and collecting final masses will have to wait until next week since our products will be wet this week. We will have labeled waste containers out in the lab. Remember, for next week, capillary tubes go into broken glass once they're used. And all of this data will be entered into a lab digital worksheet on Moodle. So on the summary slide, I said we are doing extractions and washings. What exactly are extractions and washings? Extraction is a process that selectively dissolves one or more compounds into a mixture, into an appropriate solvent. So this yields what sometimes is termed an extract. You've probably heard of that in common vernacular. For our purposes, we're typically trying to transfer a compound from one liquid solvent into another liquid solvent in the organic lab. You can use an extraction to separate a compound from impurities. And the way to do that, you have to make sure that the compound is more soluble in the second solvent than in the original solvent. So we'll discuss that later in the slides. Since you're introducing two solvents, your two solvents have to be immiscible. That means they're not soluble in one another, okay? Which also lends to the fact that they will be capable of making two different layers. You're going to mix the two layers together to maximize surface area and to encourage the transfer of your desired compound into the second solvent. Travis has made a video illustrating how to do this, and I have the still caption of one of the illustrations from your lab book that I'll discuss with you in a few slides. Washing is the reverse process. Basically, you are trying to pull impurities out of a first solvent by introducing a second solvent. So in washing, the desired compound is left in the original solvent. In extraction, the desired compound is left in the second or the new solvent. So really, extraction and washing is a terminology difference in what your objective was with that process. So here we see figure 1 from your lab book illustrating what extraction is. So you see the empty circles that are in the top layer. Your top layer is your original mixture that has several different compounds in it. And because this is an extraction that's being illustrated, the bottom layer shows our desired compounds in that unfilled circle being extracted into the bottom layer. For washing, which is what we see in figure 2, we are removing the impurities, the filled in circles, from our original mixture into the newly introduced solvent. So your lab book has a little bit about determining scale. Effectively, the size that we're working with today is considered larger quantities, and so it is called macro scale. The main difference in determining scale is what glassware you would use. For macro scale, you are going to use separatory funnels. Our separatory funnels are actually fairly small. These can get to be quite large and be working with almost liter amounts of solvent or multiple liter amounts. The separatory funnel is illustrated in figure 3 over here on the right of the slide. We see the stopcock down towards the tapering bottom of the glassware, and the stopcock is used to close your separatory funnel or open it so that you can drain your layers out. If you're trying to drain layers, you must make sure that you do not have a lid in the top part or a stopper in the top part of your separatory funnel. Travis should have highlighted that in his video as well. If you're doing something that is very small scale using milligrams amounts of material, then you can do separations in test tubes and do your washing in test tubes, your extracting in test tubes, and separate your layers using a Pasteur pipette. So in choosing a solvent, you have to have two immiscible liquids. We've discussed that already. Traditionally, in an separation, one of your solvents is going to be water. At the very minimum, you need to have a very polar solvent, and your other solvent should be nonpolar. Traditionally, we see that being some kind of hydrocarbon solvent, like hexanes, an ether, or some kind of halogenated solvent. These two immiscible compounds, since they do not have similar properties, these two immiscible compounds will create two liquid layers. And again, we see that illustrated in that separatory funnel illustration on the right side of the slide, a top layer and a bottom layer, very distinct from one another. The more dense solvent is going to be on the bottom layer. And of course, you can look up densities. Usually they're in your lab book, but you can also look up densities using the techniques that we had described at the beginning of the semester. Previously, we had mentioned that you would need to mix your two layers together to encourage the extraction or the washing, whichever process you're trying to do. It increases surface area. So the way that you're going to mix it, you're going to put a stopper in your SEP funnel. Make sure that your stopcock is turned parallel to the lab bench, and you're going to invert your separatory funnel, holding your hand, holding the stopper in between your fingers to keep it in the SEP funnel while you invert, and you just kind of gently shake and swirl. Sometimes you will need to vent, and in fact, as a good rule of thumb, I always vent in case gases get formed. If perhaps there's a reaction happening in the separatory funnel, which we'll discuss later, you certainly don't want to trap those gases. It can actually build up enough pressure that it shoots the stopper out the back. And then of course you have to start over because all of your solution has poured out onto your hand. So once you have done your mixing, you will put your SEP funnel back into the ring stand. It should easily separate back into the two layers so that you can drain off the bottom layer. Now, we said the more dense layer, the bottom layer is the more dense solvent. And that's what we see illustrated in figure 4 and figure 5 here. We see water being the polar solvent in both of these illustrations. Figure 4 is showing our nonpolar solvent being an ether or hydrocarbon, our less dense organic solvents. And figure 5 is showing your nonpolar solvent being dichloromethane, or one of your halogenated solvents that is more dense than water. While we can use density to predict which one of our layers is correct, or what the identification of our layers are, you should still use a water drop technique to confirm which layer is which. To do this, you'll get your glass pipette, pull up a little bit of water, and introduce just 1 or 2 drops of water below the surface of the top layer. You don't really want to pipette a full milliliter of water in. That's not necessary, but you'll carefully watch what happens to the water droplet. If it's more dense than the solvent it's been introduced to, you'll see the water droplet go down to the bottom layer. And if you're dropping your water into the water layer, like in the case of figure 5, then you won't see anything happen to the water droplet. It will just kind of become one with the layer. The key thing to remember in a separation is always save all your layers. As long as you don't get rid of a layer, your compounds are somewhere in a beaker or a separatory funnel for this lab. Sometimes your layers don't totally separate as well as you would like, and this is usually caused by a suspension of small droplets of one of the liquids in the other liquids. So your two layers have gotten very finely divided, and they've created what's called an emulsion. And we see a picture over on the right of an emulsion. You see your top layer is clear, your top layer is clear but yellow in color. Your bottom layer is totally transparent, no color. And then in between, it looks like there's a third layer that's kind of white. That's an emulsion. They are typically mistaken as a third layer, and they're often kind of cloudy or opaque in nature. Emulsions typically will separate out, but they can be very slow and we don't always want to wait on those. So you can add a sodium chloride solution, which will help salt out the emulsion. You can also kind of gently swirl. Sometimes just that gentle motion will help separate out those small droplets from one another. You can also add more of your organic solvent. Sometimes simply doing that will pull the small droplets of organic out of the aqueous solution. And a worst case scenario, which I've never honestly ran into, you can filter to remove small solid particles. I have, however, had to let an emulsion separate out overnight. That shouldn't be the case in our lab, but sometimes emulsions can be very slow to separate regardless of what we do.